Thanks so much for being here. I hope I make good use of this hour for you guys. So obviously, it's a pretty intimate workshop, so we can make it as interactive as we want, or I can just speak for the next 5 hours. So super happy to be at Converge22, representing Alchemy, specifically the developer education team at Alchemy. Let me see if I can take this off, move it around a little bit, because I'll be here most of the presentation. Just a little background on like who's the guy who's going to be kind of talking the most for the next hour. My name is Al, short for Alvaro Luken. I'm a software dev by trade, but I have also done a lot of teaching, specifically software development teaching, specifically smart contract software development teaching. So I worked at an education company that was me in the previous education company, Swag, called ChainShot, and we were recently acquired by Alchemy. We were Alchemy's first acquisition, or I mean, this happened maybe 4 months ago. So we've been Alchemy's first acquisition and only one at ChainShot. So we're now ChainShot by Alchemy, and we're very happy. So, and a little personal background, I started mining ETH in 2017, so I've been around this space a little bit. And fun fact, I just deactivated that ETH miner a couple of weeks back because of the merge. And if you want to stay in contact, that's my Twitter. Cool. So for the agenda for today, and I'll make sure to ask a bunch of questions such as like, you know, who's done Solidity here? Who's done smart contracts? So that we can kind of tailor this a bit more for you guys. I want the highest impact for you guys here today. So the agenda for today is we're going to write a bunch of smart contracts using Solidity. So using the Solidity smart contract programming language. What smart contracts? Because I feel workshops all the time say, hey, we're going to write smart contracts today. And then they just kind of throw you. So we're going to actually do real life use case smart contracts. 3 outlined right now. We're going to do an escrow-enabled smart contract, a vending machine one, so a smart contract that logically functions the exact same as a vending machine, and if we have time, a simple DAO. Where are we going to do these? So you can choose to write along with me. You can choose to follow along. It's fine. If you're kind of thinking this guy's going to make us download a bunch of local dependencies and softwares, no. We're going to use Remix IDE, which is completely in browser, for testing, development, and deployment of smart contracts. And it's used in production by many engineers today. So, but first, before we dive in, let's recap some Solidity 101, kind of ground ourselves with the programming language, and some smart contracts 101. That's my favorite part, because usually when I cover Solidity, people usually go like, yeah, I've done Solidity. And then when I cover smart contracts, they go, yeah, I've done smart contracts. But I like these slides that I have in here because I cover kind of early origins of smart contracts. It's only 1 slide or 2, but it's good history. So core concept number 1 is Solidity. So this is where I ask some questions. Who here has programmed in Solidity before? Raise your hand. Okay. Wow. Awesome. Amazing. You're at the right place. I had a bunch of follow-ups expecting some raised hands on that, but that's perfect. So we'll take it. We'll definitely kind of dig into the fundamentals a bit. And what I'm thinking is like half an hour of slides and me talking, and hopefully you guys asking questions. Like, feel free to raise your hand, interrupt me, go like, hey, what is that? Or you're wrong. I'm used to that last one. So, cool. I'll first look at Solidity. Solidity is an object-oriented programming language. I know this sounds kind of, and as a bit more of background myself, I only learned a bunch of this stuff like maybe 2 years back. So I'm right there with you. It's an object programming language, very much influenced by other programming languages, and I bolded JavaScript because Solidity looks eerily similar and acts eerily similar to JavaScript. So if you know JavaScript, you're going to be good to go for Solidity. It was specifically designed by the Ethereum team. If you guys read The Infinite Machine by Camilla Russo, highly recommended book. She chronicles the origins of Ethereum from day one, who did what, fly in the wall. It's excellent. But anyway, Solidity, She has like a page or two in there where they're like, the early team is deciding, do we want Ethereum to be supported by an existing programming language like, I don't know, JavaScript, right? And they were kind of talking about the trade-offs. Trade-offs ended up being, let's design a brand new one that accounts for specific Ethereum features, and that's Solidity. So properties is statically typed, which is a bunch of mumbo-jumbo saying you have to declare variable types at the beginning. It supports inheritance, which again, more mumbo-jumbo saying you can actually declare smart contract inheritance chains, parent-child inheritance chains. You can use libraries and a bunch of other cool features. Anyway, and it's the programming language used to write smart contracts. It's a programming language. There are many of them. A lot of developers have their own preference. I obviously prefer Solidity because it's the only one I know. So more core concepts, smart contract. And there's no emoji for smart contracts or contracts, so that's like a scripture one. So smart contracts, this is what I meant by like, it's just one slide, but I like it because it grounds us to the history. So smart contracts were originally ideated by Nick Szabo, one of the early crypto pioneers in the 80s, 90s, and he defines them theoretically as a set of promises specified in digital form, including protocols, within which the parties perform on these promises. And that's Nick Szabo in 1996. So he's kind of the one that termed the smart contracts as we know them today. And then he kind of adds a little addendum, like, however, smart contracts may not be smarter contracts. If you want to dig further into that statement, I will share the sites link. I apologize for not doing that earlier. I totally meant to. But these links are linked to those papers. But that's the paper name in which he kind of originated the term. So now let's approach smart contracts via Ethereum. So what is Ethereum? How does Ethereum view smart contracts? So just reading off, a smart contract is simply a program that runs on the Ethereum computer. So we used to do chain shop boot camps, and we had a whole day dedicated to grounding every student to the fact that Ethereum equals a computer. So in terms of education, we found that is the most useful way to see it. Ethereum is just a computer. It's a global one. There's only one of it, but everyone in the world can use it from any monitor ever, like the internet. Ethereum equals a computer, and a smart contract is just a program on that computer, like the programs that you double click and they launch and they bounce on the little nav bar. So the smart contract contains a collection of code, otherwise known as functions, and data, otherwise known as state, that reside at a specific address on the Ethereum blockchain. And these are written in Solidity, but again, there are other programming languages for smart contracts like Viper and whatever. So mainly, we'll cover those written in Solidity. Why? Because Solidity is an EVM-compatible language, so Solidity is perfect for this type of kind of Ethereum computer. Solidity is very similar to a class in other languages. Sorry, not Solidity. Smart contracts act very similarly to classes in JavaScript. So for example, if you're writing a JavaScript program, you say something like class, animal, open brackets. This is very similar in which you say contract, animal, open brackets. It's very similar. So my favorite properties are that smart contracts are immutable and deterministic. It took me some time as a student to understand these properties, but immutable is you launch the program on the computer and no one will ever change it if there are no clauses in the contract, in the program, that allow for permission. So you launch it once, it's immutable, it's not going away ever. Deterministic is basically that the program, no matter who uses it or where, all the users will get the exact same outcome out of using the program. It's transparent, it's up there, it's 1 + 1 = 2, no matter if I do it or you guys do it, it's still gonna be 2. And that's a stark difference from like centralized, Facebook, you may click on the button that you see in your user profile today, and it'll take you somewhere, and then tomorrow it'll maybe take you elsewhere, because they shipped an update. And more properties that I like on smart contracts, the first one being my favorite, hailing from a Mexican background, these are permissionless. So that means anyone in the entire planet can deploy or use smart contracts. The only requirement is they must have some ETH to pay the gas fee. That's it, ETH and internet. But these smart contracts act in a permissionless way, very much like the internet. anyone can go onto a browser and type facebook.com. It's permissionless. Anyone can do it. Once they get further into facebook.com, that's where they start hitting permission gates. And smart contracts are composable. Once you deploy a smart contract to mainnet, for example, Aave, Chainlink, any of these cool companies, they've deployed smart contracts, and basically you can see them as like, open APIs. Anyone in the world can use those smart contracts. Anyone in the world can hit and send data to those smart contracts. So they're composable. Cool. The vending machine. Last slide, and then we'll cover a bunch of Solidity. One quote from Nick Szabo's article that I introduced first is, he mentions, a canonical real-life example which we might consider to be the primitive ancestor of smart contracts is the humble vending machine. And we'll dig into why. So he does it more elegantly than I'll do it here. But basically, he just breaks down a vending machine is a machine. It has some logic. And everyone kind of expects that machine to do one thing or another given some conditions being met, right? So it's very simple. You have some money, you select a drink, and if you satisfy the conditions of the machine, the deterministic outcome is there's a drink coming to you, right? The logic is programmed into the machine, so a smart contract, like a vending machine, has logic programmed into it, right? Very simple. And we'll actually do a vending machine smart contract today, which is always really fun, a little useless, but it's fun. Cool. So Solidity syntax basics, let's see. I actually don't need to get behind here real quick because we're not going to write, we're doing good on time, which is good. We're not going to write smart contracts till like the 30. And I'll try to get you guys out of here as soon as possible. Let me do another kind of check of the room. Who here has programmed in Solidity before? Raise your hand. OK. We got one more Solidity power user, 2, 3. OK, cool. 4. Awesome. And who here, just to actually touch the follow-ups, which I wanted to, who here has written a smart contract before? The first one and the second one are kind of tied together? OK, cool. Who here has deployed a smart contract before? All right, one power user. Cool, OK. Hopefully, we have time to do all of that today. So again, you're more than welcome to follow along. We'll start coding in like 15 minutes, but laptop is required for the coding element. Otherwise, one thing I will mention, I freaking love Solidity because when you write out the smart contract fully, it's actually more legible than the legalese contracts that we're used to in the traditional system. Like from here on out, party A will therefore be known as none of that crap. It's just code that is very legible. And you can go, OK, so there's one party, there's two parties, this party can do that, this party can do that. So that's what I like about contracts. That's why you don't need to code along. I feel you'll be able to kind of follow along intuitively. Cool. So Solidity syntax basics. And since we have time, does anyone have any questions so far? Kind of been rushing through the slides. Let me know. I love questions. Love discussion. Yeah. Yes, I planned to do that before, but I forgot. Yes, I'll definitely share the link. Yeah. Sure. So you're asking if the contract might be insecure because it's Turing complete? Yeah, for sure. That's a good way to see it. I mean, Turing completeness gives you basically a garden that is not walled. There's no walls ever, so you can either build some really cool shit or shoot yourself in the foot while you're building that cool shit, or be malicious. It's a walled garden. There's one of the early founders, Gavin Wood of Ethereum, talks about this really well, where he's saying like the server, and I use this metaphor because he uses it, the server, the traditional like Web 2.0 server is a walled garden of innovation. If you want to innovate, you have to go to Facebook. If you're Zynga and you want to innovate, you have to go to Facebook, ask them permission, ask them API keys, ask them all these things, and then you innovate, and then Facebook just rug pulls you, right? And then I know this is not directly tied to Turing completeness, but Gavin Wood says this, and then he kind of references Ethereum's open kind of architecture in which anyone can do anything. So yes, Turing completeness allows you to do all the good things and all the bad things. Yeah. Hey. Yes?
I'm not technical, but so this might be a dumb question, but
No dumb questions.
canonical, you used another word for that. Why do you
So canonical, as Nick Szabo mentions it? Yeah. I'm actually not sure. Like canonical, is that like, I don't know, is that like, you know, there's sequence to it? Is that what he means? Set in stone. Okay, okay, like canon. Okay, there we go. Yeah, that's elegant. I mean, yeah, the vending machine kind of is the ancestor to the smart contract. I think that's what he's going for. Yeah. Cool, guys. Love the questions. Please keep them coming. Just anytime I'm saying anything, just raise your hand, please. All right, cool. So some Solidity syntax basics. We're going to go through the basics with like a simple smart contract. So first off, and if this seems like off to you at all, don't worry, because we'll ground it back when we actually get all of these basics into a smart contract that we write together or that we write each. So the first line of any smart contract in Solidity and Ethereum that you'll see ever is this like little comment SPDX license identifier. That's the first line you'll see, and that's just declaring a license for the smart contract. Good stuff. Pragma Solidity is the second line you'll see in every smart contract that you see. That's just declaring the compiler version for the smart contract. I call those two lines the boilerplate lines. I hate them because as a developer, you have to like be copy pasting them everywhere, and like, you know, I just want to write the contract. Okay, so boilerplate stuff, and you'll see that we just copy paste them when we actually end up writing. So this is what I meant by the class, you know, the contract looking very similar to class structures of JavaScript. To declare a contract, you just do contract, and then the name of the contract, open bracket, close bracket, and that's the scope of your contract. Easy. Cool. A little more on like the versioning for the Pragma Solidity line. This I'll just do quickly. I don't want to spend too much time on this, but Solidity uses semantic versioning, you know, major, minor, patch, right? The only reason I bring this up is Solidity is still on major version 0. So the minor versions, you notice how it says 0.7.5? The minor versions act as the major versions right now. The Solidity devs plan to roll out major version 1 when they feel Solidity is ready. So we are early. Oh, there's a little laser pointer. Okay, so cool. The constructor. A lot of programming languages have constructors. And the TLDR is, this is a function, this is a line, this is some logic that is only run once ever when the smart contract is deployed to the chain. And then it's thrown out. It's actually not part of the contract once it's deployed. You know, you push it up, the Ethereum runs that logic in the constructor and then throws it away, right? And it's usually like initial state setup logic, right? And we'll dig into that. You can have state variables in your contract and initialize them to values. So here we have two Boolean state variables, is happy and is sad, and we're assigning some state to them, right? Because you know, the contract is the contract, but we can also store specific state on the contract, right? We can store whether is happy is true or false, or whether is sad is true or false, and Ethereum, the Ethereum computer, is nice enough to store these values for you at that contract address. So one thing that I want to distinguish here is, here it says bool is happy. That's our variable declaration. That's totally fine. If we add a visibility identifier in between, in this case public, Solidity will do some cool stuff for you, such as creating an automatic getter function on the contract. So if you want these variables to be very open, you know, these are composable APIs, right? How like accessible do you want this data to be? At the end of the day, everything on a smart contract, since it's on the open chain, is accessible. But you also maybe want a meter who can see what, how easily, right? So if you had to put public, everyone in the world can see it, and it's just really easy to be indexed because Solidity creates a getter function, which a lot of services end up using. And we can also set these state variables in the constructor. So as I mentioned, the constructor usually adds as like an initial state setting thing. So if you're deploying your contract in the constructor, you can pass in the value that you're feeling at that time, and it will assign it to the state and then throw out the constructor, right? I know these examples are kind of like, why would I want to deploy a contract and pass it a true parameter that's going to be assigned to the isHappy state variable? Well, we'll see, because in the contract, in the constructor, we can do a lot of cool kind of initial setup stuff. Solidity also has numbers. It has uint and int data types. Uint x equals 10, and then int for negative and positive numbers. Int y equals negative 10. Solidity has all the familiar math operations or operators that we're used to. Good stuff. And then all of the Solidity data types, I hope we touch on a lot of them today. Boolean strings, numbers, bytes, address, and payable. This is wrong. Address and address payable. These are the most important data types that you will learn in the week. This is what the address and address payable types are what distinguish Solidity to be a smart contract language, right? Because when they were saying like, maybe we can use JavaScript, yeah, but like you'd have to create like a whole kind of custom thing to account like for an address. Whereas if you created a programming language from the bottom up, you kind of built what an address is into the compiler. So enums, arrays, mapping, structs, all these cool things. And all data types have a default value, meaning if you don't assign anything, there's no operator, like equals operator, they'll just get assigned their default value. So good stuff. OK. The address keyword in Solidity. So Solidity supports the address and address payable types. They're more than just strings. So when you declare a variable as an address, you're telling it it's a, I believe, 20-byte string. But it's not just a string. It's 20 bytes that is an EOA or a smart contract address. And Solidity knows that behind the scenes. It's cool because this type gives you access to, if it's an address on the chain, you're able to actually query its balance in real time in your code. So you can say, I don't know, you can even do something funky like, if the function that a user is calling is like mint NFT, you can do something funky like, if this user's address .balance is less than 2 ETH, like don't let them mint the NFT. You can do anything, right? It's an unwalled garden. So, but you have access to some special types on the address. That's the cool thing about the address. This is like the second or probably number one most important thing that you'll learn hopefully this week. MSG.sender. MSG stands for message. And you can do funky things in your logic like, if MSG.sender equals this address, do this. If MSG.sender is not equal to this address, do this. And we'll do that today a lot. So MSG.sender tells you who is currently sending this transaction, who is trying to hit this composable API, right? Because when you send a transaction to a smart contract, for example, if you mint a Bored Ape, you're sending a transaction to the mint function of the Bored Ape smart contract, right? So that smart contract gets your hit, and that hit contains information on you, specifically MSG.sender, who's sending that hit. And then MSG.value is, in the contracts, you also can send some ether. So if you minted a Bored Ape, I don't know, it was like 1 ether or whatever, you send some ether as part of that hit. So this is able to say, out of the current transaction hitting my contract, how much is it sending me, right? Because maybe you send a message.value that is lower than the required mint amount, and you get denied. Other important features, and then I think we're doing good. Require is basically a shortened version of an if statement. It will revert the transaction if the Boolean of that condition evaluates to false. So this is really useful because if you don't want people going where they shouldn't go in the terms of your contract clauses, you just revert the transaction and nothing happens. Nothing changes the world state of Ethereum. They just lose some gas, worst case. And then payable is a flag that you'll find added to certain functions. Payable just says, hey, this function can accept ether. If there is no payable flag on the function, it will completely revert. It won't allow you to send ether. Cool. And I have some suggested reading, which is why I wanted to share the slides as well. All of the places I pulled from, Mastering Ethereum. If you read that front to back, you'll be in a great state in terms of Ethereum. Cool. So now we're going to dive into Remix. Yeah, question. Yeah, good question. So you're saying when you have a contract deployed and people are hitting it from all these places, You're asking if the state of the contract is shared or if, right? Yeah, good question. So no, the smart contract. So the smart contract is shared amongst all of us. So we're gonna build a vending machine today, and we're gonna initialize like the number of sodas to whatever we want. It can be like 100, and all of us are gonna, or we won't have time today, unfortunately. But if all of us buy a soda, we'll decrease it by about 30 or so. But that's the same state that we're all affecting collectively. There's no new instance created. Yeah. It's good stuff. Ethereum is a singleton computer, which is kind of like the mind breaker of this all. We're all affecting not just the contract. Well, the contract state is singular, but also like the global state of Ethereum. It's kind of nuts. Okay, so we're gonna. Oh yeah. Sure. Sure. Mm-hmm. Right. Mm-hmm. Mm-hmm. Is this clarification to his question a little bit as well? Mm-hmm. Right, for sure. So we're bringing up the fact that within a function, when your transaction hits it, we can write, and we can see right now, we can write variable declarations or initializations in that function, which act as local memory during the life of the transaction. So we'll see it a bit more firsthand in Remix, but a mint transaction runs your logic from top to bottom, and once it hits the end of the function, it stops, right? And your transaction gets mined, and that affects the world state of Ethereum. But in that singular case, you are still privy to local state in that function. It's good stuff. Yeah. Cool. All right, let's dive into Remix. So this can either go really well or really bad. Let's hope it goes well. So I'll close some of this. I wish I had like a shared chat with all of you guys so I can send the slides and stuff. But Remix is just remix.ethereum.org, and it's quick startup. So it's good stuff. I'll introduce the interface real quick. We're doing good on time. I believe we'll have time for 2 smart contracts, which is good stuff. So, or hopefully 3. So let's see. All right. And then the last slide was a Remix IDE plus the vending machine. So the first contract we're going to do is a vending machine. It's good stuff. All right, so let's jump in. And in this default workspace, and let me know if like the audio is weird or anything. If you can't hear me, just let me know. In this default workspace, we're just going to select new file, create new file, and we'll call this the vending machine .sol. So every Solidity file, smart contract file, ends in .sol. Cool. So let's start off with the boilerplate, which I hate, because if I had my flow, I'd just start writing the contract. Contract vending machine, right? And start our scope. But I need the freaking boilerplate because it's really annoying. So let's do SPDX license identifier, and then I'll do MIT. I'm not a good license guy. I just know that one is like friendly for education. And we'll do pragma for the version that we want this smart contract to be compiled in, pragma solidity, and I like 0.8.4 because I feel that's where I learned a bunch of my things. And cool, we have the initial setup for the smart contract, easy, right? There are many flows you can choose to write your contract. We can go declare the state variables first or put up the constructor first. Let's do state variables first. So we can do a uint, and we'll make this public, num sodas, right? We want a num sodas. We want this smart contract to function exactly like a vending machine does. So we want ownership, right? Vending machines are owned by people. So let's do an address public owner, right? And I believe that's it. Like, we can do more cool stuff. We can do anything, right? We can do like address public, like engineer, right? And the engineer will have certain like permissions that normal people don't. Whatever. We'll leave it up there. I don't think we'll use it. But okay, we've got our state. Now it's time to start filling up like the logic of the contract. So we can do a constructor up there, and then the constructor is scoped, as is all kind of the code, functions and constructors and contracts are scoped entities. So in the constructor, let's say, and then as a quick recap on like general programming, whatever goes in between those parentheses are parameters that you pass in when you call these things, right? So we're saying at constructor time, at deployment time of this contract, let's accept a uint parameter called numsodas, and let's just do numsodas now. And notice I put a little underscore before it so that it doesn't, the compiler, if I do this, it will complain. Because I already have a state variable called numsodas. It's just going to complain. So we need to make it something slightly different. And what we'll do is, at constructor time, initialize the number of sodas in the smart contract state to whatever we pass in. Yeah?
Yeah, so just quickly, I know you already mentioned this, but uint versus int, what's the difference there?
Yeah, for sure. So uint is only allowed to hold positive numbers, and int pretty much also holds negative.
Okay, there's no other difference?
No other difference. I decided not to go deeply into like number types, but uint is actually an alias for uint 256, meaning it holds 256 bits, right? Bits of data. But you can also do cool stuff like uint 8, uint 16, stuff like that. But yeah.
Cool, thank you. That's all I need.
For sure, for sure. And we'll probably, like in the voting system that we will write if we get time, hope we do, we end up using an int variable for a proposal that might get negative votes, right? So if we're voting on a proposal, maybe some people decline that proposal, so we need the negatives. Cool. All right. And so we declare our numsodas, and then what we're going to do, this is the first instance where msg.sender pops up, the most important thing in Solidity. We'll do the owner of the machine. Let's initialize it to the msg.sender. So what this is saying is, once we whoever deploys this contract to the chain, whoever pays gas, let's make him the owner, which logically makes sense, right? And we're actually kind of like halfway there. We've got kind of the state. We've got the initial state set up. What else? Like we can do some cool stuff, like require that the numsodas is greater than 0, even though the uint kind of takes care of that. Okay, so now let's do a function, and the first one that comes to mind obviously is like purchase a soda. So a function called purchase a soda, and we'll scope it. And also another thing I do, if you guys have Remix pulled up, and I didn't introduce the interface like I said I would, ignore this little scope glass. This is the compiler section, so you'll be able to see specifically what compiler your smart contract is, and this is the deployment section. If you want to deploy your smart contract to testnets or mainnet. It's really cool. Hopefully we have time to do that. And then one thing I'll note is, especially as we're learning, turn on auto-compile. This is like incredibly useful. As you're writing, it'll keep you honest. So say, I did like msg.sendy or something, and it'll immediately go, whoa, not sendy, right? Sender, and then be happy. And then here, it's complaining probably because I'm not adding a visibility to the function. Who can call this function? Who can call this composable API? Let's just make it anyone in the world can buy a soda, right? Public. And we don't go into it today. There's many different types of visibility that you can play with as a developer. Public is the most friendly, obviously. So if you guys remember back to the slides, I mentioned the payable flag. So since we're going to be purchasing a soda with ETH, we need to add the payable flag as well. Otherwise, this purchase a soda function will not accept any transactions that carry Ether with it. And cool. We'll do the require statement, which is the shortened if else statement, and we'll do require that the msg.value, require that the transaction hitting this endpoint has greater than 1,000 wei in value, right? So this soda, we're setting the minimum amount to buy soda, 1,000 wei. And that's it. Super powerful. So now you've conditioned, if you rig this function up to a button on a front end, a user would click it and their MetaMask will pop up and pre-fill the value to 1,000 wei. So that's what this require statement does. Because MetaMask, if you guys didn't know, it runs a simulation of your transaction before you do it. That's why sometimes you get like, hey, this transaction is probably going to fail. Cool. And then simple stuff like, once the 1000 way is covered, we can just do num sodas minus minus. That's it. Just bring the state down because someone purchased a soda. Easy stuff. This gets deposited directly into the contract, which brings me to my next point. Like, okay, like this is kind of a vending machine. It's done. Let's ship it and let's celebrate. But once we all make like a trillion billion dollars, we'll all celebrate, and then like someone in the room will say like, wait, how do we withdraw this? And then everyone's gonna like, ooh, and that has happened before with like millions of dollars. So beware of the logic that you lace into your contract. You want to make sure that you provision it with logic to withdraw funds if you so need to. So we can do function, withdraw like profits. And we'll do, sure, let's make this public. We don't need a payable flag because this function does not expect any ether. And the cool thing about not adding the payable flag is if it gets hit with ether, it'll just say no, revert. And then withdraw profits. And another use of the require is we can require that the only person, even though the function is public, the only person that will be able to get past line 20 without a revert is the current owner stored in the state variable. That's really powerful. So obviously we want only the owner to withdraw their profits. And then once they get past that, let's put the logic to actually send the owner profits. Solidity does like a weird logic where it's to.transfer and then the msg.value. That's the syntax. So we'll do owner.transfer and then the address.this balance. So that's just funky mumbo jumbo to say whatever this contract holds, dot balance, send it to the user, to the owner, right? And then we're kind of done. We're doing good time. That's great. One more provision is if we want this vending machine to be like Nick Szabo-esque and act like a real one, we want this to meet the same like laws of physics that a real vending machine meets, even though this one is better because this is not confined to space. So function change owner, we want the ability, like if you own a vending machine in real life, you want to be able to actually sell it or give ownership of it to someone else. So let's do that here. Let's do change owner. Is this visible, guys? Is this okay? Okay, cool. So thank you. Let's do change owner, and this function will accept one parameter. So the owner will call it and say, this new owner is who I want to take over for me. So we'll do public, and it's really simple. One, we'll require, let's just copy paste this line. Obviously, we want the ownership to only be the owner. Otherwise, we're delving into like traditional contracts where anyone can do anything. So require message.sender equals owner, and then we'll just do whoever is the owner, just store the new owner into it. That's it. And then that will affect the contract state, and then that new owner will have access to all the owner logic from now on. And that old owner is MIA. So cool. I believe that's it. Any questions on the vending machine, guys? We have a couple others to draw up, but this, yeah.
So you mentioned that earlier when the variable is set, like it's set to public, it gets like a default getter.
Yes.
Does it also get a setter?
Good question. That's very like familiar programming. No setter. You have to implement it yourself. He's asking if while we're making these public, Solidity adds a getter, which is basically, a getter is this. Function, get owner, public, and then it just return owner. I'm not going to write it out fully, but Solidity does that for you, and it doesn't take lines to do it. It just kind of adds it in there. No setter, you have to do it yourself, or the default value. Yep.
Does it actually call the getter by the variable name with get in front of it, or is it run as just a dot property?
Good question. Actually, yeah, that's my bad. No get in front of it. It's just, if you want to call it from like some indexing service, you just have to do something like address, like dot address, right? And Solidity would kind of do the rest for you. Yeah.
How do you inspect these variables or debug the code?
So that's where visibility is very important, because once we deploy these, let's see if I can bring up like Etherscan. And once we deploy these, this is a block explorer. I should have probably saved an already deployed contract, but I'll just look at the DAI smart contract, DAI being the stablecoin. Once we deploy them, DAI is a deployed contract. So like I said, guys, the first lines, besides like more commenting and stuff, you'll ever see is the compiler declaration and stuff like that. Yeah, wait, why was I here? What was the question again? Sorry. Oh. Right. So two answers. One, you can inspect the variables in any way. So say you need the variable num sodas in the withdraw profits, you can just do, if num sodas is greater than 10, right? And num sodas is a state variable, and it's in the global scope of the contract, so you can use it throughout all your contracts. So that's the programming answer. And then to inspect further values of variables, once they're deployed and their visibility is right, indexing services will do cool stuff like this, right? And you'll be able to actually see what state is held in these certain variables. So let's see, like, I don't know, decimals, I guess, has 18. The name is DAI stablecoin. All these things are coming up because they're data types that are like array. Sorry? Total supply, yeah, I'm not even sure. Like number 9, yeah. I would believe with a stablecoin like DAI, yeah. But yeah, these are all public variables, and Etherscan has the getter kind of indexer rigged, so that once you deploy a contract, you can see the values. Yeah? Yeah, for sure. So he's asking if there's any way to kind of like filter, kind of maybe what's called more like a user error. So if someone, for example, fat thumbs it or fat fingers it and sends 1,000 ether instead of Wei, there are ways to say, if they do it, they do it. But you can do something like require that the message.value, something like that. So equals exactly 1,000 Wei. Otherwise, no go. Right? Which makes more sense actually in the scope of this. But I just do greater than because sometimes it's a little annoying. Just, send 2,000 Wei or whatever. But yeah, good question. Yeah? Yeah. So he's asking if public functions can include, user kind of defined data. Yeah, for sure. That's the parameters. And there can be a billion parameters in here, should we want. Yeah. Cool. All right, let's do a second smart contract. Let's do an escrow. I love escrows because they are actual real life utility. So for like, I don't know, my grandpa was always like, oh, you work in crypto and it's a scam. I'm like, okay, let's do an escrow contract, and we write it together and it's all good. So cool, let's do a new file and we'll call it escrow.sol. So who here is familiar with what an escrow-based transaction is? And it's okay if you're not, because I was not. Okay, a couple of folks. So an escrow is basically a three-party transaction. It's a two-party transaction with a trusted third party in the middle. So if I am trying to sell, what's your name, sir? Trip. A Trip? Trip. If I'm trying to sell Trip an ASIC miner, so I have an ASIC miner, Trip wants to buy it, but someone has to do the handoff first. Either he has to give me money first, or I have to give him the miner first. So that creates immediate distrust. Obviously, it's easy since we're in the same room, and we could just do it. But what if we scale over to the internet, and we're talking from our own locations, and we're talking all the shipping stuff? Someone has to do the first thing, and that's where trustlessness is needed. So we're going to write up a contract that allows us to do this sale transaction in a way that we can breathe and be kind of safe from either me scamming Trip or vice versa. So cool. Escrow transaction. Let's do it. So I'll just copy paste the boilerplate stuff out of the vending machine. Escrow.sol. And then I'll do contract escrow. So the reason I say this is super real life is because this is actually super real life. We are in 2022, and there's no way to transact across the internet between two parties that don't know each other. There's just no way to do it unless you do centralized service and pay a fee somewhere. Anyway, I'm passionate about this one because the ASIC case happened to me. Okay, state. Let's lay down state first. It's a three-party transaction. We'll do address public for all of them, and we'll lay it down. First one is the beneficiary. This is the person getting paid. And then address public, the depositor is the person selling, right? Or the person paying, selling. No. Let's just do person paying. Whatever type of transaction. It can be any type of transaction. And we'll do an address public arbiter. And this arbiter is who Trip and I designate. Like, maybe Trip and I are across the globe, right? Maybe he's in Europe and I'm in South America, but we both know someone that we both trust via our own independent routes, right? So we'd probably designate him as arbiter. That way, if Trip tries to do something funky, I can just say, yo, arbiter, he's doing some funky stuff, let's revert this, and he can do the same, right? So, it's the trusted third party, but in the best of ways. All right, and then constructor will do all the initial state setup, and we'll pass in the address of the beneficiary and the address of the arbiter. And we'll declare everything. So beneficiary equals whatever is passed in. The arbiter is equal to whatever is passed in as the arbiter value. And then the depositor is just whoever declares a contract, right? Because I can just see, if the depositor is a person paying, I could just see someone saying, hey, relax, I'll just draw up a contract, and I'll send it over to you, right? This is the equivalent. Cool. So we have all the initial state set up. Now let's do a function. And this is actually a really simple contract. This is simpler even than the vending machine, because what happens is the settlement is performed off-chain. So I will sell my ASIC to Trip, and the arbiter, so neither Trip nor I holds any valuable goods in any point in time. The arbiter holds the money. So what happens is, first of all, let's make this constructor payable so that if I'm paying, I'm saying I'm gonna pay, and let's just clarify this, person getting paid is the seller, and person paying is the buyer, right? Myself as the buyer, I'm deploying this contract, so I'll deposit it initially, I'll seed it with the buy funds, right? That's why I made the constructor payable. So I'm gonna set all the initial state and deposit like 1 ETH as part of the deployment, and what happens is that contract will hold the 1 ETH. What do we do now is provision, the safekeeping of that ETH and make sure that it doesn't get locked, first of all. So first of all, we can do the simplest one, release funds, and we'll make this public, and we'll require that the MSG.sender can only be the arbiter. And Solidity lets you do cool things like, only the arbiter can call this, right? And this little error message will bubble up to a user, so if they're using MetaMask, they'll see that instead of just like out of gas or whatever. So require message.sender equals the arbiter. So the arbiter can release the funds, let's say back to depositor, right? We're gonna write the clauses that affect the malicious cases first. So first of all, release funds back to the depositor, depositor.transfer address this.balance, right? It's complaining because this is where address payable comes up kind of for the first time. If you, in the scope of your contract, are making some of these address types transact Ether, Solidity prefers you do that only to address payable types, right? Now it's complaining because here I'm making the msg.sender. So all that. Let's actually just cast this. We'll just say payable depositor. So this is called typecasting, and you're just typecasting it locally so that Solidity is happy. Cool. So release funds back to depositor. Now let's do the release funds to beneficiary. We can just say release funds cleanly, right? Because if the funds are released to the beneficiary, that means the transaction was successful. And we can just do this, beneficiary. And since we have a little bit of time, we can do something cool like, destroy contract, which is one of my favorite opcodes of Ethereum. If the arbiter or whoever is responsible we can do destroy contract, and what will happen is we can just do self-destruct and then pass in the address of whoever we want receiving any of the ether left in the contract. So what is it? It's mad because I'm doing the address payable thing again, so I'll cast this to payable. Whoops. Where am I? Payable, and then that. And I think that's it. But one thing is like, okay, we don't want anyone to destroy the contract because that's MSG.sender. So Trip and I are transacting, and we've got our third-party arbiter, and we're all happy. But then someone in this room heard about the fact that I like escrows and just comes in here, calls the destroy contract function, which destroys a contract. The self-destruct opcode, I didn't even introduce it, but basically it just demolishes, it pushes the code of the smart contract off the chain. It deletes it, which is good. But maybe let's just do something more like require that, we can start playing with more flags of logic. Like, for example, bool, public, like transaction approved, right? And we'll initialize it to false. And so when we release funds cleanly, we can do transaction approved equals true. That way we flip the switch on the logic flag. That way the destruction of the contract cannot occur until, what was it called? Until transaction approved is true, right? And that is an escrow contract. That should work for any cross-global sale, settlement. My roommates and I were talking the other day, like we have some stuff that we kind of want to do. We all trust each other, so we don't need this. But I don't know, maybe like for something long-term, like the contract can hold some ether and pay us out on like, very agreed upon logic, which would be really cool. And this is like the basic building block of all the cool protocols that you've seen at this conference, like Aave, Converge, Aave, Chainlink, all these things. This is a basic building block. 3 people, what they've done is scale it up, right? So, yeah. Sorry, a smart contract, what was the word? Right. Good question. So he's asking if you call the like self-destruct on one contract, like one in effect like some other contract, like what are the chances of that? The chances are basically infinitesimally small because a contract address is actually derived from the user deploying it plus like some great source of randomness. So there's like very little chance that there's a collision. And if there is, we have to be afraid. But yeah, we delve into the numbers where it will take trillions and trillions and trillions and trillions and trillions, like I have to say trillions like 1,000 times more of years to maybe find something, an occurrence like that. Yeah. Well, the address there's no play, the address doesn't affect anything here. The self-destruct, once it gets hit, it'll just say this smart contract, delete it. There's no there's no address in this equation actually, which is interesting. But yeah, the address is not affected. It'll just remain there and you'll actually be able to still see it in block explorers, but you won't see anything. It's just like, it'll just say, you'll click contract and it'll say like 0, there's nothing there. Yeah.
The address you're passing there isn't the address of the contract, right? Or the address to send the rest of the money to.
Correct. If there's any. Yes. Only yourself. And that's really, I mean, they made it that way so that even if the contract has some like dust, like 0.000, like one way, you'll still get it if you just self-destruct it because there's no like protocol logic to just destroy ether all of a sudden. That's only the burnage that occurs. Or you can lock it away. You can deploy a contract without a provision to withdraw the funds, and that's basically a burn as well. Yeah?
Would it be better in that case for the void contract to have like a Boolean value for that you can set for a board if we've got, I forget what you do for the thing, like release funds back to depositor where you set a state for that and you have a destroy fund, like a board contract or something. Because that would destroy the contract and push it back to the sender anyway, right? If that's what the other.
Sorry, can you clarify?
In other words, you have the contract being destroyed if the contract is approved,
If
but
the,
not if it's aborted.
no, this is completely standalone. Yeah. So I just included that logic just to say, you know, why would we want the contract there? We wrote it in a way that it's only like a one transaction contract, right? Because we deposit at deployment, and then we destroy it once that transaction is settled off chain. But we can definitely,
Sense to destroy the contract regardless of whether it was deployed, approved.
Right, that's what I mean.
It's only in one of the two cases you destroy it.
gotcha, yeah, okay. So,
You don't have a contract aborted flag and have it killed that way, and that destruction then send the money back to the sender, rather than you sending it back to the sender, but then leaving the contract floating around.
right. Yeah, so this should take care of that case now. So any action that occurs on the smart contract will trigger a flag that says this is safe to destroy. Yeah.
One basic question, how exactly are these methods called?
Yeah, good question. So for example, I'll kind of take the easy way out on the answer. You can use a block explorer, and you can go in here, for example, a DAI stablecoin. It has this write contract functionality. And what this write contract functionality does is it exposes all of these functions to you. So for example, say, I don't know, the transfer. Who here has transacted in DAI before? All right, a couple folks. We've called this function directly. We've called it, MetaMask usually abstracts this from us, because what happens is, let's say like you go onto something like, I don't know, Alchemix. So Alchemix is like a DeFi protocol that I really like. You do something like, I don't know, you hit a button, right? And that button is rigged up in the back end to pop up MetaMask and say, do you want to perform this action or whatever? So that button is triggered into the contract address of DAI. So if we're writing a website together that is just solely for transferring DAI, we'd create a little button. And when the user hits it, we rig it up to this DAI contract and kind of help the user fill in these values via their MetaMask. So the address of the, I'm assuming this is the receiver, and how much WAD is used throughout stablecoins for some reason. It just stands for an amount. So we can send 1,000 DAI to a recipient address. And you can actually do it via here, right, by the way. I don't think this will pop up because it's going to complain that my formatting is not correct or something. I actually don't have MetaMask set up here. But, oh, it did pop up. OK. So I guess it popped up. But yeah, that would be one of few answers. Yeah?
Yeah, so just a quick question. So I've heard about this having the arbiter, this scenario for like many years now. What is an example where this is actually used in reality? Where is it like actually deployed?
This type of logic?
Yeah, that type of logic.
Yeah, for sure. The first one I think of is Aave. And I have 2 minutes, so I'll try to like TLDR it. Like Aave is basically what banks do today, like Chase, JP Morgan, whatever. Aave does exactly the same in a permissionless, decentralized, global way. So, yeah, don't know, did you?
Oh,
No.
That's good. You still have someone in the center though.
Yeah, but it comes kind of
It's faster, it's easier, it's better.
Yeah, I mean, because if I trust you to be the arbiter, that's great. That's kind of like more local. But what if we decentralize the arbiter further? So it's like a court of arbiters, right? And like a majority of that court needs to approve that transaction. And that's where we fall into the rabbit hole of like, okay, what if we don't want a court? What if we want like, a DAO or DAI holders to vote, Yeah, it's good stuff. Yeah. Cool, guys. Any last questions? We have a minute left. It's been fantastic being here with you guys. Yeah?
So the versioning system needs a minor, so does that break anything backwards, or does it try to only add features?
Good question. So the question is like, with this semantic versioning type things, if we wrote all our smart contracts in 0.8.4, right? The question is, if we change this to, for example, 7, what types of effects do these kind of like updates have? So yes, to answer your question, a higher update does tend to break lower versions. So for example, 0.7.4 does not have integer overflow or underflow protection. What that means is if we do something like 1 plus, blah, 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 a super big number, 0.7.4 will not protect you from it, but 0.8 will revert your transaction because you're overflowing. So yeah, it tends to backbreak, but new features are added for the developer traditionally. Yeah, good question. Yeah, last two questions. How do I, so if we had more time, if we had an hour more, we'd be able to do so many cool things. So if you want to deploy this, I'll leave this to you as a personal challenge. Remix has an excellent deployment interface. All you have to do is rig up your MetaMask. I would do it now, but I don't have my MetaMask installed. This is my work computer. Rig up your MetaMask, pull up Remix, and what Remix allows you to do is choose any environment that you want to deploy it to. So I believe the injected provider is the MetaMask. So MetaMask has you choose a network that you want that MetaMask to point to. So you can either choose a test network, or you can even choose a mainnet right here. And MetaMask integrates right into Remix, and it will read your account and let you set, this is all deployment. So we can deploy our contract with, I don't know, that amount of way, and that's our escrow, right? So we deploy it, and it even segments out what data you want specifically. So like the beneficiary, you can just plug in an address here. I'll just so it kind of looks neat, I'll just plug in the DAI address, the DAI contract address, the arbiter, and then transact. Hitting that button. So I actually just deployed this, but on the Remix virtual machine. So it's just, it's deployed. But once you do that, if you rig it up to MetaMask via choosing injected provider, your MetaMask will pop up, you'll pay some gas, and then it'll deploy the contract for you. Yeah. And I believe we had a question here. Yeah. Yes, that's a good question. He's asking on like the nature and on the nature of atomicity, which is good stuff. Transactions are fully atomic. They either happen successfully all the way or no. So yeah. And last question, sir?
I was going to just ask about Remix. The virtual machine then will simulate whatever version you told it to do at parts compile, and you can sort of test your code locally before you push it to market?
For sure. So I actually deployed this on the local VM, and notice it gives you the whole contract right here, like in a very kind of interactable way. I love this. This is composability at its finest. You just click some buttons, and the VM will react in a way or another. Perfect for testing. No gas, no nothing. It's just a little local blockchain that is spun up. If I close this page, it just dies. Well, cool, guys. I'll leave it on the last slide. Thank you so much. Follow us on Alchemy platform. Follow me, and yeah, thank you, guys. Yeah, thank you so much.